So what we have here is our, you guys had that worksheet yesterday on area and volume ratios. Well, Tuesday, you know what I mean. One of the problems was number 8. It says wastewater technology, a 75 millimeter pipe discharges 2,000 liters of wastewater in a given period of time. If they want to upgrade the pipe to discharge 3,000 liters, what size do they need to use? So obviously the 75 is a dimension, it's a length, it's a diameter. It's this page that looks like this, by the way, that we're working on. It's just a single page. It has, the triangles and shapes on top, and then word problems on the bottom. It says page 250, chapter 6 on top. Exercise set 6.2. Okay, so we have a ratio of lengths there, which is the 75. We're going to relate that to X. The 2,000 liters and the 3,000 liters appear to be volumes, but are we capable of changing a volume in this problem? We're not. All we're doing when we increase the diameter of that pipe is we're increasing a cross-sectional area of the pipe. So what we're really working with here is an area. To change a volume, we would actually have to also change the velocity at which the water came out of the pipe. We can change the length and the width by changing the diameter, but we cannot change that depth. So this is just a ratio of areas. So what we're going to do is we're going to turn that ratio of lengths into areas by doing what? How do we change the ratio of lengths into areas? Square it. Square it. Remember, you square the lengths to get the ratio of areas. So 75 squared is 5,625, right? X squared is X squared. Now, that's our ratio of areas from the lengths. So we're going to equate that to the 2,000 over 3,000. Now I can make life a whole lot simpler by just reducing that to 2 over 3. So we're going to solve for X squared here. We are going to just cross multiply and divide. So 5625 times 3 divided by 2 gives us 8437.5. So X squared equals 8437.5. What do we still have to do? Square root. So X equals the square root of that. Second square root, second answer. 91.86 millimeters. So we'd probably do a 92 millimeter pipe. So like I said, like I mentioned the other day, is you have to be careful. Even though liters here looks like a volume, really all we're changing is an area, cross-sectional area. Similar issues with other problems here. Give me just a second to write that down. 91.86. With number 9, a steel bar. This steel bar is 38 millimeters on a side. So 38 millimeters, 38 millimeters. And it's some stock length. Has a mass of 22 kilograms. And then they want to compare that to another steel bar that is 19 millimeters on a side. Also the same stock length. They want to know what the mass of that is. Well, we all know that mass is related to volume. The bigger the volume is, the bigger the mass is. But did we change the entire volume here? Remember, to change volume, we have to change all three dimensions. Did we change the width? Yes, we did. Did we change the height? Yes. Did we change that depth or length? No. So we did not change a volume here. We only changed an area again. So we went from 38 to 19. That's areas. Now, I'm going to reduce that to 2 to 1. Both of those divide by 19. So it's a 2 to 1 ratio of areas. Is that correct? No, it's a 2 to 1 ratio of lengths. The length went from 38 to 19, or the width went from 38 to 19, however you want to look at it. It's a 2 to 1 ratio of area of lengths. The ratio of areas would be that squared. 2 squared is 4. 1 squared, 1. So we have a 4 to 1 ratio of areas. In our mass is going to be affected similarly. 22 kilograms is the larger one. Cross, multiply, and divide. 1 times 22 divided by 4 is a 5.5 kilogram bar. What do you think? Good stuff? No? What if I gave you something like this? Pretend those are similar shapes. One's just an enlargement of the other. And let's say this goes from being 4 inches up to being 10 inches. And I tell you that the volume of this one here is 650 cubic inches. How would I find the volume of this one? Ratio of lengths is going to be what? Okay, we got 4 to 10, which does reduce to 2 to 5. Very good. Now we're comparing here volumes, so we need a ratio of volumes. How do we get that ratio of volumes? Cube it. 2 to the third power is 8. 5 to the third power, 125. Where's the 650 go? On the bottom. It's from the larger figure goes to the larger number. 8 times 650 divided by 125 gives us 41.6. That is inches cubed. If you had done 10 over 4, then the 650 would go on top. Doesn't matter if you reduce. If you didn't reduce, you'd just have 64 over 1,000. Works out to the same ratio. Okay, you guys are going to get a quiz on this stuff, but I'm going to hold off and give you the quiz at the end of the hour and then let you guys go because I've got to get out just a couple minutes early. So we are going to talk about the packet that we talked a little bit out of the last class on Tuesday that has all the measurement, adding, subtracting, multiplying, dividing on the front. We talked a little bit about like problems 31 through 34. 35 and 36 are pretty much the same too. I want to take a peek at like problem number 37 and start on from there for right now. Number 37. Everybody still have that packet somewhere? We are going to end up with a lot of packets this semester, so find some way to organize. You might want to get a a small folder just for this class so you can keep them all together. So number 37 out of this packet. We have a simple truss with a span of 32 feet. We're given a 512 slope. That's all we're given. We are asked to find the height, and then J here is the common rafter length. Now, even though this is a truss, they still often refer to that as a common rafter length. The proper terminology in truss is the top chord length. So it means kind of the same thing. It's just when we do some of our other calculations for hip roofs and valleys and stuff, they still refer to it as common rafter length for those applications. So now here we have that 512 slope. That really is a triangle. It looks like this. It's a right triangle with a height of 5 and that base of 12. And of course that compares to this triangle here. I could have drawn it the other way and did the triangle on the other side. It really doesn't matter. So on this big triangle here in the truss itself, what dimension do we know? Yeah, the span is 32, so half the span is 16. If this is a common rafter, common truss, both sides are symmetrical, so it's just half the span. So we have that 512 slope. 5 represents the rise. That's the H is the rise. 12 represents the run, the horizontal, that's the 16. So we find H by, perfect, cross multiply. 5 times 16 is 80, divide by the 12. Gives us 6 2/3. Now at this point, you guys should be getting closer. You start to recognize 6 2/3 feet is really 6 feet and how many inches? 8 inches. Very good. Some common fractions, I think I went over these at the end of last semester too, but some common fractions you should start to be familiar with. 1/4 of a foot is how many inches? 3. 1/3 of a foot is 4. 1/2 a foot? 6. 2/3 of a foot? 8 inches. And 3/4 of a foot is 9 inches. Now, if you get a lot more experience there, you might even start to notice, 1/8 of a foot is 1.5 inches, and so on. I'm not going to make you go into the eighths of a foot, but you should know the quarters and the thirds of a foot. Or should be getting to where you know those, and you can do the quick conversions between them at some point here. So we have that height of 6 foot 8 inches. Now I'm going to keep that 6 2/3 feet because I still need that to do my common rafter. That common rafter comes off of this triangle here, which is the same. It's just the mirror image of that blue one I did. So I've got this is 16 feet here for the run, and I got that this is 6 2/3 feet. Notice I went back to the fraction of feet because to do that, to find that hypotenuse, what are we going to do? I'll do the square root of 16 squared plus 6 2/3 squared. So we'll punch that in. Second square root, 16 squared plus, my calculator doesn't do fractions, so I've got to do that. And I get 17.33333. 17 1/3 feet. So that common rafter length is 17 feet and 4 inches. Let's do another example, but let's step it up a notch. Why not, right? That first one was not horribly realistic because it came down to points here on the ends, right here. It came down to points. Trusses don't do that because there's thickness to the lumber they don't necessarily come down to a perfect point. We have something called a heel height. That heel height is the height at the end of the span to the top of that top cord of the truss. Now, most of the time, that's just there to account for the thickness of the lumber. A common heel is you add a 1/4 inch to whatever that diagonal cut across the 2x4 would be. So the heel height depends on your slope. The reason you add a 1/4 inch, by the way, we got that top cord that comes in there. The bottom cord butts up against it like this. They add a 1/4 inch right here. They leave a 1/4 inch on this edge of the board, and the reason for that is strictly practical. When they use their auto saws to cut those, if they try to cut directly into the corner, when the saw hits that corner, it often deflects the blade off to one side or the other. So by cutting it, leaving that 1/4 inch there, that makes a cleaner cut. It gets a more precise cut. So you have this 1/4 inch plus the thickness of the 2x4. But then they go up to type A heels, which is the thickness of a 2x6 plus a 1/4 inch. And then there are advanced, energy heels where they'll go up to 12 inches, so you can get your full 12 inches of insulation all the way out to the edge of the attic and things like that. Because that is an issue. You can see that the insulation coming in here hits the top cord and it gets squished down on the very outside edge. So anyway, let's say, just for the sake of making this easy on us, that this has an 8-inch heel. This span, we're going to put it at 36 feet. We're going to give this a slope of, let's go 8/12 slope. And once again, I want to find the height, and I want to find that top cord length. To find the height here, we got to do a little bit of sketching, because our slope will not give us the height directly. Our slope is going to give us this blue triangle. This is a right angle. I'm going to call this dimension here A. It's not equal to H. And of course, what's this dimension down here? 18, right? Half of the 36. And we're going to compare that to the 8/12 slope. We've got 8/12. Where does the 16 go? Or the 18 go? On bottom. That's the run. It goes with the 12. It's also the run. We cross multiply and divide. We get, this is 12, isn't it? That is equal to A. What's H? Yeah, we got to add the 8 inches. It's 12 foot, 8 inches. J. To get J, though, we go back to that blue triangle. That blue triangle was just 12 feet here and 18 feet here. So to find that top cord length here, it's the square root of what? 12 squared plus 18 squared. A squared plus B squared equals C squared. So second square root, 12 squared plus 18 squared. Now we're going to get an ugly decimal here, 21.6333. We're going to round it to 3 decimal places, 21.633 feet. Do you guys remember how to convert that into feet and inches? And let's say we're going to the nearest 16th of an inch. That's 21 feet. We don't change that. Take 0.633 feet. Have to turn it into inches first. It's feet right now. So 0.63. So what I'm going to do is, in my calculator, you see I've got the answer still there? I'm going to subtract out the 21 feet. It's gone. So I have the 0.6333307, whatever. I'm going to multiply that by 12 to turn it from feet into inches. I get 7.5997, right? So that 7 is whole inches, right? So I'll subtract that 7 and it's gone. What do I do with the 0.5996? That goes times 16 to make it the 16th. So that's 9.5. Is that going to be 9 or 10? 10/16, which will round to 5/8, or reduce to 5/8 inches. So that top chord length is 21 feet, 7 and 5/8 inches. Does that look sort of familiar doing that feet, inches, and sixteenths? Okay. On this packet, I do want all of your measurements reported in feet, inches, and sixteenths. So the nearest 16th of an inch. You might run into something like this with overhangs on it. We've ignored overhangs so far. Let's say this is a 10-12 slope. Let's give this a 30-foot span. And I'm going to keep it simple and give you 2-foot overhangs. We want to find the height, and we want to find that top chord length. Notice that top chord length includes the overhang now. Complicates life just a touch. So to find our height here, we're going to have this blue triangle again. This is H. What's this bottom piece going to be? 15, half of the 30, right? 15 feet to there. So we find H by doing what? (10/12), that's our slope, right? H/15. H is the rise, 15 is the run. Perfect. We'll cross multiply and divide. 10 times 15 is 150. Divided by 12 is 12.5. H is 12.5 feet. So in other words, H is 12 feet and 6 inches. Now, do I use this triangle here to find J? No, because I have 2-foot overhangs. I have to make another larger triangle to find J. The only piece I know about this larger triangle is this bottom piece, which is not 15, but 17. It's that run plus the overhang. So I'm going to have to find a height there. I'll call that A for now. So I'm going to do the 10/12, my slope, equals A/17. 10 times 17 is 170. Divided by 12 is, oops, what happened there? It's going to be 14.1667, right? So A is 14.1667. So to find that common rafter length, that's the height I have to use with 17. So the square root of 14.1667 squared plus 17 squared. So now I still have, oops, I don't still have that in my calculator. There, now I still have it in my calculator. So what I'm going to do is I'm going to do this. It's the square root of, I'm going to use that answer. Second, square root. I'm going to use the answer key to enter that in as the answer squared. So it's the square root of the previous answer squared, so I don't have to type that back in and round it off. Plus the 17 squared. And it gives me 22.129 feet. Well, again, we're going to list that as 22 feet. Then what are we going to do? We'll subtract the 22, and then times 12 to make it into inches. So that's 1.5, so we're going to put 1 there, and then subtract the 1, and times 16 to get those, how many sixteenths? 8.7, so 9 sixteenths. What do you think? I didn't have a heel in that one. Came to a point here. There will be some where we do combine the heel, but I'm going to see what you can figure out on those. What I want you guys, what that's basically going to do for us here is going to bring you up to number 60 in the packet. So you'll be able to calculate those. You're going to get some work time later. But anybody have any questions on how we found those measurements? It's just pretty much similar triangles and a squared plus b squared equals c squared so far. Now, the next thing I want to talk about is something called a hip roof. You know, your typical roof has a gable end, and the roof goes off however, right? Let me do a better job of drawing that. Still a bit of a elevated view of the roof. Something like that. That's your typical roof. And your only roof surfaces are the two sides. That's a common roof. Well, in a hip roof, what do? They take the ends of it and they cut them back like this, and they slope them. They do it to both ends. They slope them off. So now we have to worry about how, not only framing up the regular rafters, but how do we frame up this corner and those little pieces that are going to be coming off each side. I do have a model here that I'll grab. This thing right here, and it is pretty super, you're right. This is a hip roof. This is how they look. This is how they're framed up. Is you do have that master rafter down the corner, and you have, these are called jacks. The short ones that come into that corner rafter are jacks. They're shorter than the commons. So you remember, you got your common rafters here in the main roof. You have, this is your longest jack, and then you have your other jacks. So let's sketch this out from a top view. By the way, anybody who's looking for some extra credit, I do have some other models I need built. So if you are interested, come talk to me and I'll let you know what I'm looking for. So if I'm looking here at a hip roof, this part here is the main roof. This would be considered the common rafter. This right here is called the hip rafter, sometimes referred to as the corner rafter. Have you guys covered this in your framing at all? Yeah. Print reading a little bit? Okay. Then, of course, on either side, any of the ones that hit that corner rafter, that hip rafter, those are called jacks. And then you have the longest jack. The longest hip jack. That one's actually very important because as a relationship, in some cases, as a relationship to our common rafter. What we're going to look at today is a common hip roof, or sometimes called a conventional hip roof. In a common or conventional hip, both slopes are the same. So let's take a little picture here again. So if this is my hip, if this slope here is 612, this slope here is also 612. Both slopes are the same. So let's say we have those 612 slopes and we have a span here. We'll give ourselves a little bit more room. A span here of 32 feet. What I want to find, my goal here, is to find I'll number them here, find two things. One, longest jack, and 2, something called the jack rafter decrease. I'm just going to call it the jack decrease. Okay, the decrease from one jack to the next is the same. So once you know that decrease, you can just keep subtracting it from the longest jack, you can get all your lengths. So let's do this. Step 1, whether it's conventional or unconventional for a hip, step 1 is always going to be to find dimensions of the common rafter. So kind of remember that's back here. So what we're doing is we're taking this slice out of it that is a common rafter, looks just like that. What do we know about this common rafter? Perfect. It's 612, 32-foot span. Now what we want out of it, there's 2 things that we might want out of it. We might want the height, and we definitely want the length of the common rafter. How do we find the height? Well, we've got a run of 16. So how do we find h from there? Perfect. 6 over 12 equals h over 16. We cross multiply, divide, h is 8. So now then, how do we find that? How do we find that common rafter length? This common rafter length, how do we find it? Equals that. So the square root of 8 squared plus 16 squared. We've got 17.889. Now at this point, I'm going to trust that you guys can convert that into feet, inches, and sixteenths. I'm not going to spend any time on that. So this length right here is 17.889 feet. Since this is conventional, we get to skip a lot of steps here. The longest jack is just equal to the common rafter. So this here is how long? 17.889 feet. So now step 3. Length of the next jack. To find the length of the next jack, we're going to assume we have a 2-foot spacing here, 2 feet on center. See you guys on Monday. Those 2 guys. So our 2 foot on center spacing means this next one here is 2 feet over. So that's going to give us a triangle here like that. What do I know about that triangle? Well, I know that this distance of the triangle here is, this distance here, which is what? 14. Good. How do I get 14? Yeah, it was 16 minus 2. That's 14 feet. That's 14 feet. This is my x here that I'm trying to find. And I'm going to compare that to that bigger triangle where this was 17.889 and this was 16. So I can find the length of that next jack by using that portion. 14 is related to 16, as x is related to the 17.889. So we'll cross multiply. 17.889 times 14 divided by 16. We get a length of 15.652. Nope, that's this length right here. Right? So all we're concerned about next is finding what is our decrease. The decrease is the difference between those two. 17.889 minus 15.652. That's 7,322, 2.237 feet. Now again, I'm going to trust that you guys can convert that into feet, inches, and sixteenths. So what that means is this longest one, 17.889. The next one we already found 15.652. To get the next one, all we have to do is subtract 2.237. Just keep subtracting 2.237. Now, usually the shortest jack we'll put in is somewhere around 2 or 3 feet, depending on what standard you're building by. Other things we could have found here, we could have found the hip rafter itself. This right here, that actually wouldn't be hard to find because this distance is 16 feet. This is 17.889. That hip rafter is just going to be doing that a squared plus b squared equals c squared again. Square root of 17.889 squared plus 16 squared. So 24.000. That's actually 24 feet on the dot. What do you think? Good stuff? I want to do one more example and see if you guys can tell me how to do it. Then we'll call it a day. Everybody elects Mason. So a conventional hip. This is a 512 slope. .40-foot span. Tell me what to do, guys. You got the common. And then what? Cut this as 20. Perfect. Ignore the fact that my truss is a little non-symmetrical there. Yeah. 5 times 12, 5 times 20 divided by 12. 8 1/3. So 8'4" is our height, but 8 1/3 is our 8.333. So then to find our common rafter, it is 20 squared, right? So we get 21.66, 21 feet, 8 inches. That's our common rafter. 21.667, we're going to call it for now. Feet. So what's next? I want to find the hip rafter, and I want to find the decrease. The longest, you got it. I'm going to try to draw that so it looks like it's in the middle at least a little bit. So 21.667 is the longest jack. Okay, so yeah, this is also 20. By the way, whenever it is a common rafter, a conventional hip, both slopes are the same, half the span is equal to this distance here, which is called the setback. In other words, the run of the common and the run of the hip are the same. That setback is the run of the hip. So that's also 20 feet. I'm assuming 2 foot on center spacing again. It works either way, right? That's going to be 18. This will be X. Chat. I usually put 18 over 20 equals X to 21.67. But it would have worked X over 18 equals 21.667 over 20. That works as well. Either way, you're going to multiply 18 times 21.667 and divide by 20. So times 18 divided by 20. I get 19.5 feet. So this is 19.5 feet. What's that tell me now? Careful. You're combining two processes. We're going to subtract those. So we're going to get 2.167 feet. 2 and 1 6, actually it's 2 foot 2 inches is what that comes out to be. That's my decrease. That was my decrease. Now to find my hip rafter, I don't use 18. What do I use? I use the full 20. I use the 20 and the 21.67. So I want to get that full rafter. So square root of 20 squared plus 21.667, we'll just leave it as a rounded number for now, equals 29.487 feet. And again, I'm going to convert that. That's 29 feet. What do we do here to make it inches and sixteenths? Minus 29 times 12. That's 5. We'll subtract the 5 times 16. Good. 13.4, so it's just 13 sixteenths. So 29 feet, 13 sixteenths of an inch is the hip rafter, or the corner, if you want to call it that. Did he call it a hip or a hip corner when you guys did it in drafting? Just a hip. Okay. The decrease, that does come out to 2 feet 2 inches if you figured it out for the decrease. What that's saying is to get from the longest jack, so if you want to do a schedule of jacks here, that longest jack is 21.667. That's 21 feet 8 inches. The next jack, you'd subtract 2 feet 2 inches. That's 19 feet 6 inches. 17 feet 4 inches. 15 feet 2 inches. 13 0. 10 10. 8 8. 6 6. 4 foot 4 and 2 foot 2 is probably as short as we'd go. That's all of the lengths of all your different jacks. Now, here's a brain teaser for you. 2 foot spacing here as well. What's this length here going to be on this next jack? 19.5. Since this is a conventional hip, both slopes are the same, this section here is going to be identical to this section over here. So you're actually going to have 4 sets of jacks that are identical. You have common rafter here, and of course that'll be the same length as that longest jack, but then you have 1, 2, 3, 4 sets of jacks. That's why I put that first one in black and the rest in brown. You'll have 4 sets of those brown links that you have to cut for jacks. Make sense? Okay, I'm going to give you guys another packet. So again, out of that truss packet, the measurement packet, I want you guys working up through number 60. No. The quiz is on the stuff from the very beginning from Tuesday, the ratios of areas and volumes. And then in the next packet I'm going to hand out. So in this other packet it says chapter 19 on top. That is the conventional hips. It's going to be page. Here we are. It starts on page 282, where it says review exercises. So page 282 through 283. There's just problems 1 through 3 to do there for review exercises. So I'll let you guys start working on those. I'll give you the quiz, and then we'll wrap her up.